Hi everybody and welcome to this talk. So today we are going to see how to develop reactive applications with Reactive Streams and Java 8.
Hi, my name is Brian. I'm working for Pivotal out of the beautiful city of Lyon in France and a co-working space called L'Accordé. I'm working on Spring Framework, Spring Boot, and especially on the new reactive bits. You can yell at me on Twitter with my Twitter handle, and usually I'm doing university talks with my other colleague Stefan, and today it's with Sébastien.
So I'm Sébastien Deleuze. I'm also a remote worker at Pivotal from the same co-working space. I'm a committer on Reactor and Spring Framework 5 project. I'm also working on the Kotlin integration with Spring Boot, and I'm also a Mixed conference staff member.
All right, so here's the agenda for that long university session. First, we're going to talk about reactive, what it is, why we're using it. Then we'll have a lengthy live coding session with Reactor 3. So Sébastien will show how to use a reactive library, how it works, and what kind of things you can expect to do with it. We'll have then a 20 minutes break, so you can refuel and rest. Then we'll continue with the building a reactive app with Spring Boot. So obviously this is not a presentation about Spring Boot, but we chose a runtime and an application framework to show you how you can use a reactive library in context within an application. And that will be a live coding session as well. So during the whole university session, please, if you have a question, don't hesitate to raise your hand or yell, and we'll repeat the question and we'll try to answer those as we go. And first, I'd like to ask you a couple of questions just to know. Raise your hand if you're using already a reactive library like Reactor or RxJava or AccaStream. Okay, a few hands. Now raise your hand if you're totally new to the reactive paradigm, theme, topic, whatever, and you're here to learn. Okay. A good chunk. All right, you chose the right room then. All right, let's start.
Okay, so first we usually heard a lot about reactive, that's a trendy term. So we would like to really be concrete today and ask why going reactive. I think that's more for scalability and stability than for speed. In fact, reactive APIs will add a small overhead compared to blocking one because they have to deal with back pressure and other kind of concept that we are going to explain today. But it's allowed to handle more requests concurrently, and that's why they are very, very interesting. So reactive, what is it? Reactive is used to broadly define event-driven systems. And to be more specific, we are going today to talk about reactive programming. And reactive programming is moving from imperative logic, so that's regular code when you implement your method, and when you invoke your method, the method only returns when the processing is complete, to an asynchronous, non-blocking, and functional style code, in particular when interacting with external resources that usually imply some latency and some I/O. So I'm going to show a few use cases where reactive APIs and reactive application really shines. The first one is a quite classical one. You are implementing a web application, and you need to request a remote REST web service, and you don't control the quality of service of these remote web services, that, for example, one at your customer data center, and you have to wait 1, 2, 3, 4 seconds before getting the response, and you can't cache that call. That means that your web application will use one thread doing nothing, while waiting the response, and that's one use case where non-blocking asynchronous reactive application allow to not use a single thread, block this single thread, and achieve better scalability. Another use case is serving a lot of slow clients. We live now in a world where mobile clients has overtaken regular desktop client. That means you have more clients, usually with slow connection. Think about smartphones with bad data connection. That means you will have to, with your web application, handle more concurrent requests, and here again, Reactive API really help here. Another use case is to push events to the clients. So you have an enterprise blocker like RabbitMQ that emits some messages, and you want to push these messages to the browser thanks to server-sent events or WebSockets. Again, reactive API, which are event-based, are really well suited for such push use case or for such bidirectional communication. There is other use cases like live database queries, mobile, for example, for Android UI development, big data, real-time analytics, HTTP2, and many others.
Yeah. So at that point, you're probably thinking that we're doing all of those things today, and wondering, okay, why or is JDK8 suitable for this? Is the JDK8 API good enough to handle those use cases well?
Yeah, so let's see how we could handle this without using Reactive API. So can't we just use raw Java 8 lambdas? It's possible, but you will end up with some not very well maintainable applications. Writing a single asynchronous code, a single asynchronous method is easy, but when you have to chain multiple asynchronous calls, you end up with such callback hell that is very difficult to maintain. And that's where Reactive API will help you to build some code where you can chain multiple asynchronous calls while getting a maintainable code base. So can't we just use Java 8 types? So we have Future, which was introduced in Java 5. So Future is an asynchronous type, but it's also a trap because it's blocking. To get the future, to get the result of a future, you have to call the .get method, and .get method is blocking the current thread. So don't use Future for asynchronous non-blocking application. That's not a good idea. That's why Java 8 introduced completable Future, which is a real asynchronous non-blocking type. It works quite well, but it's not suitable for streaming. Imagine that you have to receive multiple elements, you will use a completable Future of list of foo, for example, and you will have to wait that all the elements of your list has been received, and then you can begin to process your data. So obviously, that's not a good fit for stream processing. So you may think I could just use the stream class, also introduced in Java 8, and stream is obviously very well suited for stream processing, but the trap with stream is that it is not designed to deal with data coming with latency. As soon as you have I/O implied, for example, as soon as you want to expose an API coming from your database, or if you want to expose some HTTP client or server thing, that implies some latency, some I/O, and really stream is not designed to do that. And it's a very bad idea to use stream for data coming with latency. That's not the purpose of this class. We have also the good old input stream, output stream that are designed to stream byte arrays. They are blocking API. Servlet 3.1 introduced some additional methods in servlet input stream, output stream to make it possible to switch to some kind of non-blocking mode, but that's not very handy to use, not very handy to implement, and if you use a raw input stream, output stream, you are implementing blocking code, so that's not a good fit. So that's why we need tools, and today we are going to present reactive streams and reactive APIs. So reactive streams is some kind of, it defines the semantics of a reactive exchange, and it's also here to deal with interoperability between various reactive libraries. So this is some kind of interfaces that you will have to implement. And reactive APIs, the most common one are Eric Java, Reactor Core, and Aka Streams, will allow you to perform some transformation based on the data that you are receiving. So first, we are going to talk more about reactive streams. So reactive streams is a contract for asynchronous stream processing with non-blocking back pressure handling. It's a de facto standard for the behavior, defining the behavior of reactive libraries and also for interoperability. It has been co-designed by various companies like Netflix, Lightbend, Pivotal, Red Hat, Kazing, Twitter, and many others. And it's currently implemented by Eric Java, Reactor, and Aka Stream.
Yeah, so this slide is a bit dense, and it's really important. So you're probably asking yourself, what does it mean for interoperability? What does it do? How do we achieve that? What's the goal here?
Yeah, so the goal here, imagine, for example, you have a driver, database driver. implemented with Eric Java, and you want in your application use, for example, Reactor. Reactive streams allow a seamless adaptation from one reactive library to the other. And that's not hard conversion, that's adapting as the data is coming. So that really gives you the choice about the reactive API that you are using in your application independently of the reactive API used to implement your web framework or your database driver, for example. And it's allowed to deal with back pressure.
Yeah, so if two libraries implement reactive streams, they can communicate that back pressure signal to each other.
Yeah.
So we should, I guess we should explain what back pressure is at that point.
Because that sounds a little bit magic. So back pressure is a key concept behind reactive streams. So in reactive streams, you have publisher and subscriber. The publisher will publish some data to the subscriber, and the subscriber will receive this data. All this is done in a non-blocking way. So the first step for the subscriber is to subscribe to a publisher. Okay. That means that the subscriber will listen the events sent by the publisher. Then the subscriber asks one element. He requests one element, and the publisher, when he will have the data available, this is asynchronous, when the data will be available to be sent, he sends one element to the subscriber using an onNext callback. And the very important thing to understand is that publisher is not allowed to send new elements even if new ones are ready, if the subscriber do not request more elements. So the subscriber, imagine that the subscriber is currently processing the element that he has received, and when he is ready, he will ask new elements. So here, he requests 3 new elements, and the publisher will send 1 element, 2 elements when it is ready, and you see that the publisher keeps track of the demand. He knows that if he has more elements, he has 1 element left to send to the subscriber. And here, that was just a stream with 3 elements. He sent an incomplete signal to say, OK, the transfer has been completed successfully. He could also send an on-error signal to say, OK, there was an error, and that's it. So to summarize, back pressure allows you to control the amount of in-flight data between a publisher and a subscriber. It allows to regulate the transfer between slow publisher and fast consumer, or fast publisher and slow consumer.
Yeah, that one is important as well, but this is solving real production issues that you have right now, and we probably have a couple of examples for this. For example, if you've got a system with an unbounded queue, so a queue of incoming tasks or messages that you have to process, you're in trouble when the system's producing those tasks and queuing those tasks in your system. If they're faster than you can consume them, then you're in trouble because those messages or tasks are piling up, and at one point you can just either your system is broken and you'll throw an out-of-memory error because the queue is so big, or at some point the latency and the expected performance of your system is totally wrong. So that can happen, for example, if you're, even for a simple web app, if you're accepting more requests than you can actually handle, then at some point the latency will be very bad for your customers. So those are all the use cases. Basically, you're trying to push the problems away from your system. You're only accepting what you can handle. And as long as the pipeline and the stream of data communicates that back pressure information, you're always in a case where you can handle whatever you're receiving because you're communicating what you can receive. So this is solving a lot of current issues in production.
Yeah. So concretely, reactive streams is only 4 interfaces: publisher, subscriber, subscription, and processor. Publisher publish some data, you can subscribe to it. Subscriber provide 4 callbacks. So the unsubscribe for the subscription. onNext will be called multiple times each time you receive a new element, and 2 terminal signal, on error and incomplete. You can see that with subscription you could request some elements. So when you have a subscription, you could request 1, 2, 3, 4 elements, and also cancel the subscription. So this is only 4 interfaces, so you may think, okay, that's easy to implement. It's doable to implement, for example, subscriber, but for publisher, you should not implement that yourself, I think, because Reactive Streams is also a TCK, and the TCK is very hard to comply with. So that's why reactive APIs are based on Reactive Streams. That means that most of the reactive API we are going to show you just after implement themselves Reactive Streams, okay? And they have done the hard job to comply with the TCK. Reactive Streams is available in 2 distinct packages. So it's available as a standalone jar with the org.reactivestreams package. This could be used in any Java version. And it has also be integrated in the upcoming Java 9 version. In the Java Util concurrent package, there is a flow class that contains the 4 interfaces. This is exactly the same interfaces with different packages. That means that really the fact that Reactive Streams has been integrated in the JDK quite quickly, in fact, really show that Reactive Streams is here to stay. And you could use one or the other. That's the same behavior, the same interoperability, and that's a key point.
Yeah, and those packages and those jars, they don't contain the implementations, right? It's just about the interfaces. So at some point you have to get hold of an implementation, something that implements Reactive Streams. Yeah. And at that point, you can think, okay, if it's that hard to implement Reactive Streams, why don't we have one implementation, one standard of implementation of it, and be done with it? And it's actually a bit more complex because, like Sébastien said, we have 2 parts. We have the Reactive Streams part and as well the reactive APIs. And that's where each library can shine in its own way.
Yeah. In fact, Java 9 provides another class that helps you to build some publisher implementation, but does not provide itself a publisher implementation. And so, concretely, you will need a Reactive API that implements Reactive Streams and that provide a wide range of transformation, of operation available, like merge, buffer, split, transform, delay. And we are going to detail a little bit each of these Reactive APIs, and it's up to you. I mean, they have different performances, they have different APIs. So you will have to choose the best, the one that fits to your needs. So we are going to talk about Eric Java, Reactor Streams, and Reactor Core, and after that focus on Reactor Core. So this first table shows the main reactive types provided by this library. So Eric Java 1 was one of the first reactive library available. It provides an observable type that is suitable to deal with reactive types that publish 0 to n elements. At the beginning, there was only observable in Eric Java, and after that, there was a need to express that, for example, a reactive type could just emit 1 element, they introduce single, or also just communicate the complete signal. That's why they introduce completable type. Stream 2 provides source, sink, and flow types. Reactor Core 3 provide Flux for 0 to n elements and Mono for 0 to 1 elements. That's a kind of future promise type. And Eric Java 2, recently released, is a little bit more complex in terms of types. It provides 2 types for 0 to n elements, flowable and observable. We are going to see why there is 2 different types. And also single, maybe, and completable types. So in this is new table, we are going to see how these reactive APIs relate to Reactive Streams. So Eric Java 1 was released before Reactive Streams, so obviously it does not implement Reactive Streams. Observable in the latest version of Eric Java 1 provides some kind of limited back pressure support, even if it's not the full back pressure support from Reactive Streams. Stream 2 is natively based on Reactive Streams. They have chosen to use Reactive Streams interfaces inside in the implementation of the source, sink, and flow types. That means that this type does not directly implement publisher, but use it internally, and you could easily adapt to a publisher. Yeah. Reactor Core 3 is also natively based on Reactive Streams, and both Flux and Mono implement publisher. And Eric Java 2 provide a Reactive Streams type, which is called flowable. Flowable could be seen as a Reactive Streams version, back pressure ready of observable. And in the version 2, observable, single, maybe, and completable does not deal at all with back pressure and does not implement or use reactive streams. They choose to draw the line between these two worlds because Eric Java is coming from reactive extensions that is also implemented in other languages. And this is reactive API that does not support back pressure because for some use cases, for example, for some Android use cases, this is not always needed. And they choose to draw the line and to provide a reactive streams type, throwable, and other type that does not provide back pressure support. And the last table is to show you a classification not done by us, but by David Kernok. So David Kernok is a famous guy in reactive world. He's the main developer and project lead of Eric Java 2. And he also contributed the foundation of Reactor Core 3 with Stefan Maldini. So he wrote a detailed blog post when he tried to classify each reactive API. So reactive Eric Java 1 was classified as a second generation because it provides limited back pressure support and does not implement reactive streams. AkaStream 2 was classified as a third generation reactive API. It's natively based on reactive streams, and it provides some kind of actor fusion. By actor fusion, I mean that the reactive pipeline by default is using different actors, and one actor equals one thread. And they provide an optimization that allows to perform the various stages of your reactive pipeline into a single thread for better performance. That's such optimization. And Reactor Core 3 and Eric Java 2 are classified as a fourth generation reactive API because they are natively based on reactive streams and they provide operator fusion. So by operator fusion, I mean that when you define multiple steps of transformation, Reactor Core 3 and Eric Java 2 will be able to merge some operation to do some aggressive optimization of the performance. And by default, with these two libraries, everything is executed in one thread, and you have the possibility to use eventually other threads, but that's the default to use one thread. So feel free to have a look to the detail about the blog post, because like every classification like that, you need to go to the detail to know what that really means. But that's a very interesting, quite technical blog post, like usually with David, but really interesting one. We usually get the question, because we are working on Reactor Core 3, should I use Eric Java 2 or Reactor Core 3? And I like the answer from David, because David contributed to both. He's also the project lead of Eric Java 2, so we can't say him that is for Reactor Core 3. And he said, use Reactor Core 3 if you are allowed to use Java 8, and use Eric Java 2 if you are stuck on Java 6, or need your function to throw checked exception. So obviously, it's up to you to use the reactive library that you want. But for server-side Java 8 application, I think Reactor Core 3 is a good fit. For Android development, for example, Eric Java 2 is a better fit. But we will see that there is also other differences. I mean, this reactive API has not the same types, the same API, so it's up to you to choose the right one. And thanks to reactive streams, you could easily choose the one that fit to your needs.
Yeah, and if you're using a framework like Spring, we'll adapt to whatever you want to use. Yeah. So you can use Reactor 3 or Eric Java 2.
Or AkaStreams.
Yeah, or Aka.
Up to you. So today we are going to focus on Reactor Core 3, because that's also an important thing. You have to choose a reactive API. You can't just use reactive streams, that's not enough. So you will have to choose for your application the reactive API you are going to use, to learn for your application. So Reactor Core 3 is natively designed on top of reactive streams. It's a lightweight API with two types, Mono and Flux, two main types. There is other ones, but these are the main ones. It is built on top of Java 8 that allow us to do some optimization internally, and also to natively support Java 8 types like duration and other types like that. That's a single 1 megabyte jar. Eric Java 2 is 2 megabytes, I think. Focus on performance, and that's a reactive foundation. We are building Spring Framework 5 reactive support, so that's a big commitment. We are basing all the reactive infrastructure internally implemented in the upcoming Spring Framework version on that. So let me be clear, Reactor has technically no dependency on Spring. That's only Spring that have a dependency on Reactor for the reactive foundations. So let me quickly describe 3 reactive types, and we will switch to a live coding session. So Flux implements Reactive Streams Publisher. It's suitable for 0 to n elements. It provides some operators like map, zip, flat map. If you are already used to Eric Java, we have tried to reuse the same vocabulary, the same method names when that was possible. When we found some weird name in Eric Java API, from our point of view, we chose to rename them, but we have tried to keep the same vocabulary when possible.
Yeah.
And you will see this kind of diagram that's called marble diagram, and each operator in the Java doc provides its own marble diagram to explain what kind of transformation is applied. So at the top you see the timeline and the time flow from left to right. You see the various elements 1, 2, 3, 4, 5, 6 that are incoming in the transformation in the operator. The vertical line indicates that the flux has completed successfully, and when you have a red cross like below, that's because an error signal is emitted. And you see the result of the transformation at the bottom of the diagram. And you have to get used to this kind of diagram, but that's a visual explanation of each operator, and we provide such marble diagram for each operator.
Yeah, you see those all over the Reactor and even RX Java Java doc, and it's often way easier to just look at that diagram instead of reading the Java doc itself.
Yeah.
It's self-explanatory.
So yeah, that's a generic type. That means you are dealing with flux of string, flux of foo. Yeah, that's you specify the type you want to deal with. Mono, it's the same, but for 0 to 1 elements. It's also implement publisher, so that's a kind of promise future type for reactive application. That's also a kind of reactive optional, because it could contain no elements if it just emits a complete signal without emitting a value. So that can be used like a reactive optional. There is various operators. You see that we have tried to reuse names like Zen, usually used in promise type API. And it contains less operator because not all operators are meaningful for single results. So that's a much more simpler API than Flux. And the last type we are going to use a lot is step verifier. So it's designed to test easily Reactive Streams Publisher. That's the equivalent of the test subscriber from Eric Java. And at the beginning, we reuse something very close to the test subscriber from Eric Java. And after writing thousands of Reactor and Spring reactive tests, we chose to build a new API that is a little bit different, and we are quite happy with the result.
Yeah, and that type is not in Reactor Core.
Yeah,
like it's not in that jar. It's in a different jar. It's a specific test dependency.
Reactor-test jar. Yeah. So we have talked about Reactor Core. There is also an ecosystem around. So there is add-ons like Reactor Test that contains the step verifier, Reactor Adapter that allow to convert from and to other reactive types. Reactor IO provides some kind of a Reactor Netty, which is a Netty-based HTTP client and server, but exposed with a Flux and Mono-based API. So that's a kind of reactive streams-based Netty client, HTTP client and server. Eric Java and Reactor Core share the same foundation. So that's where David Carnock did a huge contribution to the Reactor project. Before and after that has been used to implement Flowable in Eric Java 2. He contributed in the Reactor organization on GitHub Reactive Streams Commons, which is a default implementation, very low level implementation of reactive APIs based on reactive streams. And that's the foundation for Eric Java 2 Flowable and the foundation for Reactor Core that provide each their own APIs based on that. And there is also Spring that shows the Reactor Core to support the upcoming reactive support. There is also fancy new stuff that we are not going to show today. So, for example, just one as an example, Reactor provides some kind of metadata that describes the reactive pipeline that you are writing in your application, and it allows us to serialize that in JSON and we have built a React-based web application that allow you to, in real time, debug and visualize your reactive pipelines. So that could be useful to monitor your reactive application.
It's very visual. You can see what happens in your system.
Yeah. Okay, so we are switching to a live coding session. So this live coding session will be okay.
Yeah, perfect. So it's based on a hands-on project. You can look it up on GitHub under the Reactor organization, and we'll walk you through it. So it's the perfect time to just look at it, see how it's solved. You'll see the totally blank and complete versions in that repository, so you can try it at home if you want. And is there any questions so far about what we've done before we switch to the live coding session? No? Good. Right.
Okay. So you will see my live coding session is very simple example to really learn how to use Flux, Mono, and Subscriber. And Brian wants will be a more complete, high-level, full application that will request some existing web services, and we are going to start very simple.
Yeah.
The idea is really to understand the reactive stream-based internal and get familiar with the API. So each part contains multiple unit tests. The unit tests are already written, and there is a to-do, and we are going to implement the empty methods to learn how to use the API. So before starting that, I want to show you when you are going to use reactive application, you are not going to create yourself usually the Flux and the Mono. You will get them from the API. So here is an example of a blocking repository. That's an interface that allows to save and to find some data in a database. So that's a blocking example, a regular one like we all use today, with void, save, t, it returns iterable or list. So that's something you should be familiar with. And if I have a look to the reactive counterpart, that's that one. So you see that instead returning void, you see the blocking one is returning void. Here, I'm returning a mono void because in the blocking version will return from this method only when the data will be saved in the database, where the principle of reactive methods is that they return immediately, and you need a way to know when the processing has been terminated. I mean, you need to know when the data has been saved in database. So mono is something that will emit a complete or on error signal to basically warn you when the data will be saved in the database as an event. Because again, the various method here return immediately. We just define the processing step that will be executed when some data will come.
Yeah, that's why we're using void, because we're not publishing any element. For the others, if it was a repository of users, we can publish a mono of user.
Yeah, for that one, we'll publish. So if it's a reactive repository of user, it will emit a user later when the database will provide it. For Findall, the reactive equivalent of returning list or iterable is returning Flux, because but that will be in a streaming way. When you return a list, you will return a list when you get all the results. Here, we are returning immediately a Flux that will begin to emit one user as soon as it is received from the database, for example. Mm-hmm. And find by ID is the same. So I'm not going to use that immediately, but I really would like to show you when you are using a reactive API, a reactive driver, you have existing methods that themselves create the mono and Flux instances, and you have to use them. Another point to notice is that we are using raw publisher as input parameter. That's the best practice, I think, an interesting one, because that allows you to use any kind of reactive streams publisher here. I mean, you could provide a mono instance to save, a Flux instance, but also a flowable from Eric Java, or use Akka streams type adapted to reactive streams to provide such publisher here. So I think that's a good idea to use publisher as an input parameter in your reactive API and use a concrete type like Mono or Flux as a return type, because if you return a raw publisher, what can you do? You can only subscribe on it. So that's not enough.
Yeah.
With Mono or Flux, you will have, it will implement publisher, but it will also provide a lot of methods to do something with the data. So back
to part one.
So the first one is really simple. I'm going to create an empty instance. That means that's a Flux instance that will just emit a complete event. No data. It just say, okay, I complete successfully. It's like returning an empty stream or an empty list.
Yeah. So when we're testing this, we are using step verifier. And so, as you understood from the previous slides, when you get a Flux or Mono or any publisher, nothing happens until you subscribe to it and you request some data. Yeah. And the step verifier is actually doing that for us in a test control environment. So we are creating a step verifier with the given Flux, and we're listing all the steps that we're expecting. So we're expecting some values to be published, then we're expecting maybe an error, or maybe we're expecting the publisher to complete. So we're listing all the steps, and then when we're calling verify, we're triggering the whole thing. We're subscribing, requesting data, and we're executing all the expectations. So that's how you can test a publisher in your own API, and that's what we'll do. We'll even use later step verifier.
Yeah. So here I'm going to return a Flux that contain two values. So for that, I'm using flux.just. If you already know Eric Java, that's a kind of method you are already used to use. So, okay.
And again, the step verifier is expecting two values, foo and bar, and it's expecting a complete signal to signal that it's done.
Yeah, and it's interesting to see that by default, I have said that you need to request the data from the subscriber to get the data. By default, step verifier is requesting long.max value. Long.max value is a special value that say, send me the data as they are available in the publisher. I could also specify just request two elements that should be green, and if I just request one, that block, because that only requests one element. So you can really control the demand. By default, we request a long max value, and you have the choice to control yourself the demand. We will see that just after. So you have various other methods. So usually that's always static methods from Flux. So here I'm going from iterable to create something from an array.
So those are all the ways. In that first part, we're creating fluxes out of nothing. Usually, like we said, you're consuming those. But here we're showing how to create those.
Yeah, and if you do a mistake like me, you will see that you will get an explicit error message that explains you that the expected value is not the right one, and that allows you to fix your test or your Flux and to get something green. Flux could also emit error, so that's the reactive equivalent of throwing an error. A throw works for blocking code because you are on the same thread. But if you are in a reactive pipeline with multiple threads, if you throw something, it will work in the current thread, but not in other. So instead of throwing an exception, you still throw exception in map operation. So in synchronous transformation, you still throw exception. But in flat map operation that we are going to see just after, you are going to return a flux.error.
So that exception will be emitted as a signal in the pipeline.
Yeah.
So you'll get a signal, an error signal with the exception wrapped in it, and that's how you get errors. And that's a way to compare the publishers, and I mean the Flux and Mono. It's a way to you can think of them as a try, catch blocks, all included. So all the logic and all the operators and the flow control for exceptions.
Yeah. Now we are going to see some Flux instances with latency. So here we are going to create a flux that will emit a value, an increasing value, each 100 milliseconds. So as we have said, you could use directly Java 8 types because it's based on that. Okay, and if I do that, that will fail. Because basically flux.interval create an infinite stream of counting values. And that's also very interesting to understand. There is some streams that have finite values, like regular list or iterable, and there are infinite streams that emit events before and after you subscribe or unsubscribe. So here I'm creating an infinite stream, and to transform it to a finite stream of 10 elements, I will use the take operator that will just take the 10 first elements, and that will match with my expectations when I expect 10 elements and then completion.
Yeah. Can you show the Java doc for take, for example?
Yeah, sure.
See the operator?
So,
yeah, so here's the kind of diagram you can see. So for take, we're seeing that we're, in that example, we're only taking the first 3 elements, and when we have those 3 elements, the operator is just sending the complete signal right away. So instead of reading a bunch of text, you can just look at those and see what the operator is all about.
Yeah. So we are going to see quickly the same thing for Mono. So same principle. You are using static methods to create instances. Okay. We are going to see an interesting difference. So this is an anti-mono, and we are going to create a mono that never emit any signal. So there is a difference because the first one emit a complete event, where this one is a mono, you subscribe to it, but it never emits any value. Okay, so that's important to understand the difference. You can also obviously create a mono from a value, like you did with Flux. But here we just provide a single value, and you could also create a mono that contains an error, exactly what we did for the Flux. Now we are going to learn to use step verifier, because for previous tests step verifier was already code was already written. So here we are going to use step verifier to check that the Flux passed in parameter emits foo bar elements and then complete successfully. So I'm using step verifier .create, that's a static method. I pass the flux I want to test, so the publisher. You see that create could take any kind of publisher. Like I said previously, that's the best practice to accept a publisher as input parameter that make it possible to test Eric Java Flowable or any kind of Aka Streams types with step verifier. And then I expect next elements, and the next elements should be at least foo and bar. Then I expect complete. And here that creates a step verifier, and then I run verify. Verify will subscribe explicitly to the publisher, and it will verify all the expectations I have written just before. So I execute the test, and that's fine. For that one, I'm going to do the same, but that's a flux that emits foo bar and then emits a runtime exception error. So instead of expecting a successful complete, I will expect an error. Okay, I provide the class, and I check that's okay. If I provide another kind of exception, obviously, again, the assertion library will say me that the type is not the one expected. Okay.
Yeah. So if you're looking at the Spring Framework code base right now in the new reactive module, we're using step verifier all over the place to test our own code, and that's the way, because it's asynchronous and things can happen in various threads. That's at least for us, that's the best way to test how a pipeline behaves.
Yeah. Now, previously we have done just simple equals comparison. Now we are going to use expectations. So we are going to use expects next matches. So here it takes a predicate. That means that the lambda that I write should return true if the test is verified. So here I'm getting some user there. I want to check that the username equals swhite, okay? But I could also would like to use an assertion library like asserg of Armcrest. So we also provide another variant, which is consume next with. Still take a user, but this time we have to perform the assertion ourselves. So here I'm going to use a simple assert equals. But you could use asserg for any kind of assertion. So here I'm going to check that the second element is okay. JC Pinkman. And I check that equals get username. Then it should complete. And I run the assertion. And that's okay. So you could use that to, with any kind of assertion library. Now we are going to test some publishers that take a long time to complete, because here we are just using some publisher that we create ourselves. But in real life, if you want to test some publisher that produce data during a very long time, so here we are going to create a step verifier that's on the Flux that expects next counts. So here I expect 10 elements, then I expect completion, and verify. So now notice, so here I'm using an interval with 10 elements emitted every second, and as expected, the test will take 10 seconds to complete. So imagine that you have, like us, many hundreds of reactive tests to run. That's a big issue to have to wait 10 seconds for getting that complete.
In your CI, yeah. And you definitely want, for example, to test timeout in your application or things that can take a significant amount of time. So when you do have that, either you wait during your CI or you need some kind of tool to do that.
Yeah. So the nice thing with Reactive API is that we could, with Reactor, accelerate the time. Because basically, internally, Reactor uses some schedulers, and he controls the tick speed. And basically, we could enable virtual time, and that will allow us to accelerate the time. A small remark here, I'm not using directly a Flux. I'm using a supplier of Flux. So why? Because you see the supplier is just a lambda that returns a Flux. That's needed because if I directly provide a publisher, if I directly write flux.interval, the flux.interval will begin to emit some data immediately. And if I deal with virtual time, I need a little bit of indirection. So that's why we need a lambda that will provide a publisher. So we are using that. Then and await, and you see that I have a flux that emits one data every second during 1 hour. So I await 1 hour, but virtually. Then I expect so much element, and then I expect complete and verify. So I run this test, and you notice that it ran very fast. I have tested a publisher that emit element during 1 hour in a few milliseconds. So that's a very good tool to write efficient unit tests with such publisher. So we are going to continue, and you are going to do simple transformation. So here we have a mono. And we want to capitalize, so this mono coming from find first, and the repository by default contain 4 users, Skylar, Jesse, Walter, and Saul, and you see that all the texts are not capitalized, and I want to capitalize each incoming data. So I'm doing mono.map. I provide a lambda, and that will return a new user with username to uppercase, user first name to uppercase, and user last name to uppercase. Okay, so that's a simple synchronous transformation. That's also important. Reactive API is not all about everything being asynchronous. You have the choice to perform a synchronous or asynchronous transformation. Here, I'm just returning a raw user. That's synchronous code, and that's not an issue. As soon as you don't have I/O and latency imply, use a map operation to do some synchronous transformation. Synchronous is not bad. Synchronous plus latency is bad, but synchronous transformation are not bad if they are used at the right time.
Yeah, and usually in your application, in your code, you're mostly use transformation operators.
Yeah.
The creation parts that we did before, it's just a way to understand how a Flux or a Mono can be created. But usually you'll just use transformation operators and more complex that we'll see later.
Yeah. So for the Flux, that's exactly the same code, the same operation. The difference is that here, this lambda was called 1 time, and here, this lambda will be called 4 times. Okay. Now we are going to transform an asynchronous transformation. So imagine that to capitalize your incoming data, you have to call a remote web services. So imagine that with a more complex scenario, obviously, but you are going to do some kind of transformation that implies a latency. That's where we are going to use not map, but flat map style operations. There is also concat map. There is different variants. So flat map transformation, it takes a user. Okay, that's a lambda that take a function that take a user, and I should return another asynchronous type, so another publisher. So I'm calling async capitalized user with my user, and you see that it returns a mono.
Yeah.
And the way it works, basically, a flat map will flatten every return user in this publisher to a flux that will emit each element emitted by async capitalized user.
Can you show the diagram for that one?
Yeah.
No, that's not wrong. Yeah, you'll see it's you're decapsulating one layer of publisher. So here, when you've got an element published, the green one, the operation will transform that green circle into those squares, and because it's a publisher itself, the flat map operation will decapsulate somehow that publisher operation and publish the square elements right on the same timeline. So when you don't want to deal with elements that are themselves publishers, then you want to use flat map, and that's quite useful in your code actually.
Okay, for that one. So now we are going to merge some data. So here we have two repositories. Repository 1 will contain 4 users: Skyler, Jesse, Walter, Saul, and it will return the results with 500 millisecond latency. Okay. So the result from repository 1 will come later. Repository 2 contains 2 users, Mary and Mike, and these results are emitted immediately. And now we are going to see the different behavior of merging the data. So if here I want to merge Flux 1 and Flux 2 elements with interleave, that means I want to merge them as they come. So I call flux.merge on Flux 1 and Flux 2. And
you see that we expect the first 2 that are emitted right away, Mary and Mike, and the others that will come later, they'll be received as soon as they come. So that's the expected behavior. Merging like this, it will publish the elements as soon as they're here. But in some cases, you want to control the order of things, even if there's some latency involved. And there are other operators to do that.
So here, basically, I have no clue that flux 1 element will come before or after flux 2. They will come as they are emitted and received. If I really want to keep the order, and you will see that when you develop some application, usually you want to keep the order, at least for some use cases. I'm using the concat operator that explicitly keep the order. Yeah. And here, you see that in the expectations, even if the result from repository 1 are coming later, they will be there. So internally, Flux is buffering the data from the first one for the second one, and it keeps the order that you have defined in the parameter order.
Yeah. But it's still triggering the both fluxes at the same time. So if you're making remote calls, all the remote calls will be started at the same time, and you're just reordering things with the operator inside. So in that case, we've got 2 users. And what are you trying to do?
In that case, I want to create a flux based on 2 mono. Okay. So basically, and I want to keep the order, so I want to create a flux that will emit mono 1 value as the first element and mono 2 value as the second element. So here, I'm also using flux concat because flux concat is taking some publisher, and publisher could be mono or flux. And so that's the way I can create a flux instance based on 2 mono. Now we are going to see how to control the demand. Remember, when I talk about reactive streams, I said that you can control the demand, so we are going to try that. For this first example, I'm going a step verifier, a regular one, that expect 4 value to be received, and then complete, and then verify. No, I just return the... Here, I just return...
Yeah, just need to return the verifier.
The verify is done in the test. Okay, now a little bit different. I will request the value 1 by 1. So what I do is that in the create method, I still pass the flux, but I specify the number of elements I want to get. So initially, here, I want to request 1 element. Then I expect the next value.
So with the step verifier, you can not only have expectations, but you can also have actions that are controlling the reactive streams behavior. So when you're requesting elements and when, if you're canceling or not, so all those things.
Yeah, so here I'm requesting 1 element, I expect that I receive Skylar, then I request 1 other element, and I expect to receive to receive Jesse. And then I cancel because that will provide other elements, and I just want to check the first 2 elements of that stream. So you see with this example that you could manage yourself the demand to verify that the publisher really work as expected. Now, that's important to be able to debug reactive APIs. Reactive APIs are not always easy to debug when you start. So in this example, I will return a flux with all the users stored from the repository. So repository.findAll, okay? And now I want to see exactly what happens in terms of signal and events. So to do that, I'm going to use the log operator. And if I execute the test, where you see that we manage the demand, where we request 1 element, we request 1 other element, then 2 elements, and we want to see how that goes. You can see in the logs that I have a log entry for each signal. For example, here we saw the unsubscribe, then we see that we request 1 element, and we see after that the onNext callback that is displayed, and then another element, the onNext callback call again, and then request 2 elements, and then I have 2 onNext callback, providing the 2 last elements, and then complete.
With that, you can see the usual issue, which is your code looks fine, but nothing happens, and it's because nothing subscribed or nothing requested. No. So the pipeline is here, but it's not being executed. So if you add log, then you'll see that you're not having any requests request signal being sent, and that's a clue that nothing is being done right now.
Yeah. So if you want to perform custom actions for each event, in that example, I will print starring for unsubscribe, first name and last name for each user received, and the end incomplete. So to do that, I am going to use the do. So I'm using repository.findAll, and I'm going to use the do on method. So do on method allow you to provide some callback to perform when you receive an event. So do unsubscribe, that's a lambda that take a subscription, and here I'm going to starring. Next, I'm doing do on next. So for each user, I want to print.
And you shouldn't use like latency involved operations in those, because those are executed on the publishing or subscribing thread. So you don't, the do on operators, they're not done for async operations. You should definitely stick to Mono and Flux for those, and use operators to merge, like we've seen. The do on, it's more like small synchronous and non-blocking operations that you want to do during the lifetime of your publisher.
Okay, so the end.
There you go.
Okay, and when you run the test, okay, you can see that the right thing is printed in the log. Now we are going to see how we deal with errors. So in the first example, we are going to return a mono of user containing the sole user when an error occurs, and if there is no error, we don't change the input. So basically, we want to replace an error case by an expected value by my application. To do that, I do a mono otherwise, and here I provide a sole user. And you see that, oh no.
It's, oh no, it's otherwise.
Oh, otherwise. Yeah. But
otherwise it is empty. We'll use it later.
We'll use it later.
And you have to publish it.
Directly the value, maybe. Oh no, that's a lambda.
Yeah, that's a lambda, yeah. So the error should be transformed into, yeah, good.
Okay, so in the test, you can see that if an illegal exception is provided as an error signal, it's returned sole, and if I just provide scalar, it provides scalar. So you can do the same with Flux. So with Flux, that's called on error resume with. So we have tried to choose name depending on the behavior. So here, that's also a lambda, and I provide a Flux that provide sole and JC that time.
So you can think of those operators as is one operation is failing, you can switch to another publisher. So for example, different API or a different repository. If you look at the diagram maybe for that one, for the otherwise, for the on error or otherwise, one of those two. Yeah, you can see that if the first one publishes an error, then that operator will switch to another publisher that you've given him, and you'll still have a pipeline that does something, even if an error happens upstream.
Now we're going to show how to deal with checked exception, because checked exceptions are not always easy to deal with lambdas. So here I'm implementing a method that capitalizes each user using the capitalize method. So flux.map, okay, and I'm using the capitalize user with lambda. That's better.
Yeah.
And obviously there is so get after here exception is a checked exception. It does not extend runtime exception. It directly extends exception. So I have to catch that. And you may think I should just throw a new runtime exception, for example, to wrap it. Okay, but the issue is that you will not get a get out of here exception here. You will get the wrapper. Okay, so that's better to instead to use exceptions.propagate. Okay, with directly the exception. So that will be a wrapper like a runtime exception. So in fact, propagates return a runtime exception, but that's a special runtime exception that will be automatically unwrapped by a reactor, allowing you to emit a clean, meaningful exception without this wrapper.
Yeah, and there's a lot of value in a reactor about how to deal with exceptions with this, and as well with some utilities that we'll see later in both parts, I guess. So Reactor is making a lot of efforts to help you track down those exceptions. Where do they come from? Because if nothing is done by default, since those exceptions can happen in any thread, the exception stack trace is just useless because it can happen in some kind of callback lambda wherever, and it's not telling you where the exception happened. So with the reactor and with a specific configuration, you can really see where the exception is coming from, and you're still back to the ways of imperative programming, at least for this.
Yeah. So now we are going to see the zip operator. So here we are in a case where we have a free string flux. We have a username flux, a first name flux, and a last name flux. This element could arrive with some latency, not at the same time, and we want to create new user based on these streams that provide each a part of the user. So to do that, I'm using the zip operator that take multiple publisher inputs. So I'm providing the username flux, the first name flux, and the last name flux. Okay, and then I do map operation. Here I have a top3 object. So
that tuple is containing for each flux, it's containing one value emitted by each flux.
Yeah. If you have a look, my tuple contain T1, T2, T3, which are the next values that are received in line, and so I'm creating a new user based on T2.
Think of it as a way to combine, for example, if you're making 3 remote calls to 3 different APIs and you want to combine all of those into a single object that you want your application to consume, then that zip is the right operator to do that.
Yeah, and like previously, Reactor will buffer the data. If you are received the 2 elements, but there is one missing, Reactor will buffer the elements until it's available to run this map transformation.
The question is, what's the maximum number of elements of fluxes you can accept?
Of elements, it's configurable. I don't remember the default, but that's something you could tune if you want. Obviously, reactive API are not magic. At some times, there is some buffer internally. You could change the value of this buffer, and it's up to your application to configure that. We have tried to provide sensible defaults, but at some point, you need to put some limits.
Oh, so what's the maximum number of fluxes you can accept in the signature, in the method signature?
Yeah.
So we've got several variants until like 5, 6, something. 6, and then we've got iterables to deal with more. It's just a way to optimize things, but 6 is the magic number here. So you can have more.
Okay, so here I'm going to return the first.
Okay, when 2 monos are competing, you want just to return the fastest one. You don't care which one is completing first.
No.
So 2 APIs may be returning the same thing, and one you just want the fastest to use the fastest value returned.
There is the same for Flux, where it's called first emitting. Okay, and here I provide the two flux, and here it's the flux that emits the first element before that will be used for all the elements. That's not mixing. Basically, the flux that emits the first element win and will be used as a source for the returning source. So for the returning flux. Now that's something quite important when you are going to build reactive application. So this flux contains 4 elements. So that's a flux of user, and I want to. Sometimes I just want to explain with my type that I want to detect the complete events. Okay. So for that, I'm going to create a monovoid from a flux of user, and that's done with the then operator. So this operator will only it don't care about the various elements. It just care about the completion signal, and that allows you to communicate the information when, for example, that allows us to know when all the users has been found. And we have also a null handling. So reactive streams does not accept null values. So that's very important to understand. You can't pass null values to reactive streams. So every reactive stream-based reactive API will not accept null values. So for that, we have just our empty method. You see here I'm providing a user. Here I'm providing a null value, and what oops.
Yeah, you execute everything.
Yeah. What just our empty does is that he will create an empty mono if a null value is provided, or it will create a regular mono emitting an element if a value is provided. So that's why you find this kind of feature in optional also. That's why I say that's also kind of reactive optional.
Yeah.
And you have also empty handling. So you could also so here I want to return the same mono pass as input parameter. And emit a scalar when it's empty. So I have otherwise, remember otherwise that replace an error by a value. Here I just say if
no value has been published, for example, from a repository, you're not getting anything, then you can provide a default value that will be published instead. So that's a way. So there are ways to handle errors, to switch to another publisher, or there are ways to switch to default values when nothing has been published.
Yeah. Remember, I talked about interoperability. We are going to show concrete examples. So now I'm going to convert from Eric Java 2 to Reactor 3 without any external adapter library. So to do that, here I want to adapt from Flux, from Reactor Core 3, to Flowable, which is the reactive streams enable observable from Eric Java 2. So to do that, I will use Flowable dot from publisher. You see that it takes a publisher as input parameter. Since Flux implement publisher, that's fine. And for the other way around, that's the same thing, Flux from, and I can pass the Flowable because Flowable also implement publisher. And for my various tests, I do the conversion in one way and the other, and you see that works. Now, more difficult, I want to adapt a Flux to a Eric Java observable who does not implement publisher. So to do that, I will first create a Flowable from the Flux, and Eric Java 2 provides some conversion method internally that allow me to do the job, and observable as a toFlowable method. So here you see that I have to provide some kind of strategy because since observable does not manage back pressure, there could be use cases where you may miss some elements, so you have to provide a strategy to know if you buffer them, if you drop them, if you throw an error. So here I will use buffer, and I will create a Flux from this Flowable.
Yeah, so we'll keep those. If the publisher is publishing faster than we can consume, then the strategy here is to buffer what we've got until a certain limit, but we could just drop. And if more elements are provided that we can consume, then we'll just drop them and not process them at all.
Yeah. So now I'm going to convert from a mono to Eric Java single. So to do that, I'm using Flowable from publisher. Mono is a publisher, okay? then two observable. Then first on error, because a single could only contain one element, it does not accept empty, so if there is an empty value, it will throw an error. And for the other way, I have single to flowable, and I create the mono instance from that.
So you probably won't use those operators a lot. I think that frameworks and libraries will do that for you. It's just a way to show you that once you've got publisher under the hood, then you can translate from one to another and use libraries that are built with various libraries, various reactive libraries.
And that's really not really conversion. That's more adapting because the adaptation is done as the data are received. So that's a very lightweight operation that could be done in production. There is a very low overhead, so that's totally doable. You could also convert from and to Java 8 compatible future like that, and mono from future. Okay. Just two remaining parts, and then you will be able to drink tea or coffee. You will see Brian demo is much more fun.
You really need to understand all the operators and what you can do.
Yeah, you have to learn the basics, and after that you could play with very fancy stuff. You just get all the fancy stuff for this talk. So here, so that's very simple, but I want to get the value out of a mono. And we have called this method with an horrible name to avoid you to using it in production. It's called block. And we call that because Eric Java, I think, and other libraries call that get. And we get a lot of people using get in their code because they were new to reactive programming. And as soon as you put a blocking operation in a synchronous transformation like a map, basically you are killing your reactive pipeline and you have a big issue. So we really would like, by using this name, really show the user that's okay to do that in test, but in your production code, you usually want to avoid calling block until you are on a specific thread pool and you know what you do.
Yeah.
There is also some facilities to convert a flux to iterable. So that's to go from reactive to blocking, usually for test. And the last part is the most difficult one.
So when you have to deal with legacy code that is not reactive, then you have to deal with it in some ways. You have to deal.
So the use case is, for example, you have this JDBC-based library that using that you need to deal with your database. No reactive driver is available, and you want to integrate that into your reactive pipeline without impacting too much the performances. So that's possible, but you have to be very careful. So here, I'm going to create a flux for reading all users from the blocking repository. So you remember we had this regular blocking repository interface, and I want to integrate that in my reactive pipeline. So I want to create a flux for reading all users from the blocking repository, deferred until the flux is subscribed, and run it with an elastic scheduler. The elastic scheduler is a way to provide a thread pool, so that's like an executor service. So to do that, I'm calling repository.findAll. Okay, I'm transforming it to a flux, and then I want to. So this is blocking code. So since it's blocking code, I need to execute that in a different thread pool, because if I execute that in the current thread, that will be an issue in terms of performance. So I'm using subscribe on. So subscribe on, if we go to see to the Java doc, it runs subscribe, unsubscribe, and request on the supplied scheduler. So it will run subscribe on the specified thread pool, basically. Okay. So I giving it a way to create a specific thread pool. And if I do that, that's not enough. That will block, because basically, if I see the error message, the call to final must be deferred until the flux is subscribed. That's because in that code, flux.from iterable is executed directly in the current thread, and basically Reactor has no way to move it to the thread pool. So I need to use flux.defer.
So somehow we're wrapping that one with a different flux that will be triggered, and that will execute whatever is inside it when we're subscribing to it.
Yeah, basically that allows Reactor to wait to be on the thread pool created by schedulers.elastic, and then, since that's a provider of a publisher, it will execute that code that creates in a blocking way that transforms the iterable to a flux on another thread pool, and that's a good way to implement blocking code. Obviously, you don't want to do that in your application in a lot of time, so that will be handled by frameworks, or you will have to be careful to do a blocking to reactive adapter on top of your reactive libraries, and when you can, you will use directly reactive libraries, like there is currently for NoSQL, for example, NoSQL database.
Because if you're doing that, you're somehow using a thread pool, and you're a bit back to imperative blocking code, so you're losing a bit of the advantages of reactive applications. So you really have to pay attention to that.
Now I'm going to do the same, but for saving some data. So here that's a little bit different. Here the find all method was triggered by the subscription, so that's why we use subscribe on. Here we are going to insert user contained in the Flux parameter in the blocking repository using a parallel scheduler. So what I do is flux dot. So now I'm going to use publishon. If we go to the publishon Java doc, run on next, on complete, and on error on the specified scheduler. Okay. The previous was subscribe on a specified scheduler. This one is on next on a specified scheduler. So I specify the scheduler. So this one is parallel. Don't really care. And then I do on next. Remember the next when I was just doing some system.println, and Brian said that we need to be careful. If you do blocking operations there, you need to be careful and to be in the dedicated thread pool. So here I'm going to call repository.save user.
Yeah.
Okay, and I return
then.
Why I return then? Because if I don't return a mono void, I have no way to know the end of the processing, because we are in a reactive function, and I have to provide that.
Good.
Okay, I think we are done for this first live coding. So now it's time for 20-minute breaks, and just after that, Brian will be back with a fancy Spring Boot reactive demo based on Mono and Flux. Thanks.
All right, you're back. So after this well-deserved break, we'll talk about how to use those reactive APIs in applications, concrete applications. So our first experience with reactive APIs, that was when we started working on that field, and as well when we started working on supporting those use cases inside Spring with the new Spring Web reactive module. So we have the experience of building a framework around it, and as well using applications built with that. So the example we'll use today, so the goal is not to show you what Spring or Boot is doing right now. The goal is to show you how to use those APIs and operators and how you can apply them in an application. So you can translate that to any other framework you'd like. But just so you know, the application we're going to see is built with an experimental boot starter, which is supporting the new reactive stuff. That experimental starter will be merged into Boot 2.0, which is in snapshots right now. And Boot 2.0 will be based on Spring Framework 5, which right now is in milestone phase, so you can already start doing things and testing things. And the new 5.0 release for a framework is based on Reactor 3. So we don't often add a hard dependency in Spring. And for this, we added Reactor because we've based all our reactive support on this. All right, so the application, Spring Boot, that will be our point of entry for programming. But behind that, we'll use, obviously, Reactor, API, and Spring Framework. And just so you know, for the web part, that will be the framework part where we deal with our application. But for the web part, we're not depending on the servlet API. For Spring MVC, that's the base of the networking, communications, etc. For reactive web, we're not depending on servlet API anymore. So that means that you can use many different runtimes. You can use Netty through Reactor Netty, Undertow, Jetty, and Tomcat. So depending on the runtime, it will be a native adaptation to that runtime, or it can be done through Servlet 3.1 async IO, but under the hood. You're not exposed to the Servlet API anymore. And for some runtimes even, probably for Jetty and Tomcat, we'll probably use both. We'll try to have both native and Servlet 3.1 adapters. And those adapters and layers that I'm talking about, they're all about translating the back pressure from your application to the network. So, and both ways actually. So it means that you won't try to read more than you can handle, and you won't try to you won't be able to write more than you can write on the network. So that's the important part here. Otherwise, it's just wishful thinking, and nothing will really pan out. All right, so during the live coding session, we'll see a few things. We'll call remote REST APIs, we'll deal with data stores, we'll do some error handling, rendering HTML views, serving static resources, and do some more things like service and events. So those are the things that you're used to doing already in your applications, and now we'll do those in a reactive way. We're not supporting everything right now, we're still catching up with Spring MVC, but we're already in a good shape, so it should be still complete. All right, so let's check it out. That's my application. So I've created an application with a starter Spring.io with the experimental reactive starter, and this is a regular Spring Boot application with a few quirks because it's still in the works. I'm ignoring a few auto configurations, and we'll see why later. But it's still a pretty basic application with one application class, and as well I've added a few things here and there, but we'll see later what it is all about. So the first thing we can do is just start the application. Yay. Living on the edge, a demo with snapshots all over the place. Forgot to do something. Later, we'll use a MongoDB database. Here we are. We don't need it right now. No problem. All right. So this is our application. And we want to, this is a web application, right? So we want to have some kind of controller to show a first thing. So with our demo controller, there you go. So I've got a demo controller, all the endpoints nested under demo, and it's a REST controller, meaning all the return types, all the return values from the control methods will be directly serialized as part of the HTTP response. So what can we have for controllers? What can we, if you're familiar already with Spring MVC or those signatures, what could you expect? The first thing we can expect is to do the simplest thing that we already do, which is providing directly a string and saying something like hello devox, and mapping that on an endpoint which would be DevOps, for example. So I've DevTools enabled in that application, which means that every time I'm rebuilding the project, it's restarting and it's ready to handle new requests and it's updated. So if I do demo DevOps, okay, Okay, so you're wondering why are we doing all of this and why did we have that first part with all the mono and fluxes and we're not using those? It's because we won't prevent you from doing synchronous stuff if you know that you're not doing anything blocking. So that's a really important part. You shouldn't do anything blocking in there. So if you return directly a type, we assume that you know that you're doing, and we will wrap that with a mono or something in our framework to have that in the pipeline. So you can still do that. You can do more complex things as well. Still get mapping, and we could have a hello endpoint this time, and this time we'll have a mono type, and we'll see how. And I'm waiting for a request param with a string name here. And here, because we want to directly create something out of thin air, we can use the operator we used before, hello, here. So by doing so, we have a new endpoint.
Return.
Yeah, obviously. You still need those.
Not with Kotlin.
Kotlin, yeah. So yeah, same thing. So when we're doing this under the hood, when we're sending a request, there's the whole subscription chain. The whole execution chain is being built by Spring. We'll have all the operators within the framework, error handling, etc. ready, and we'll just chain your execution, your controller, right in the middle of that pipeline. And your pipeline will be triggered only when the request comes, is subscribing and ready to get the response ready. And when you publish the data, it will be written as it goes to the network. So that's how it goes. And to really show you more, that's the simplest thing we could do. But if you want to really get your hands dirty, you could use the low-level API, and that's what we'll do. And you'll see it's different. So we have a new concept of exchange in Web Reactive, and you'll see what kind of things are involved here. So for now, I'll just do this, but that won't be the case. You'll see how. I can ask the framework to inject that server web exchange. And that exchange contains both the request and the response objects. Those are not servlet related. Those are new interfaces within Spring, and that's the abstraction you can use to do HTTP work. So if I'm getting the exchange.getResponse and extracting this now. Never know how to. No, never mind. So server HTTP response. So we can get the response like this. So usually you can do things like set status code. We can say that it went well, that we can use the headers and say that we want the set the content type to a media type text plain, something like this. And now we need to publish to really write the body. And that's where we need to have an actual publisher. We won't provide a string or an object like this. We need it to be a publisher. We need to provide a pipeline that the framework will subscribe to and use it to write to the response. So if we look at the actual write methods, we've got write with and write and flush with. So the write with is the simplest one, and it requires a publisher of data buffer, and I'll explain what it is. And the other one is a variant, and it's for more advanced use cases where you want to really control the flushing on the network. So you're providing publishers of publishers. So every time one of those publisher is completed, we're flushing on the network for you, and then the next publisher is being used to write more body, and then when it's done, we're flushing for you. So that's a way to really control how the data is written on the network. But for now, we're just use write with. And we see that write with is returning mono void. And it goes back to the first part with Sébastien, where we said that when we want to know when something is done, we're using that mono void return type to really signal we're done. So we'll change this to mono void to signal, to tell the framework when I'm done dealing with the response, because I'm dealing with things manually. And now we're waiting for, we need a publisher of data buffer. So I can't use string directly, because in our case, because we have a really efficient runtime with a really efficient reactive API, we want to be more efficient as well. So instead of copying and allocating a lot of memory for strings, etc., we are using data buffers. And this is an abstraction that can translate to regular byte buffers, but as well buffer abstractions in some runtimes, just like Netty or Undertow. Those buffers are optimized, and they're made to be reused, recycled, so you're not allocating memory too much. You can really use a direct memory. So this is all really optimized, so you don't have to allocate, reallocate, and create a lot of garbage. So this is, if you deal with those things at a very low level, you can have a very, very efficient stack. But here, because we're in demo, usually to create buffers, you don't create them out of thin air. You need a data buffer factory. And that factory, for the demo, I'll just create a default one, which is creating byte buffers under the hood. You can ask it to say, I'd like to create direct memory buffers. You can have more options, but here we'll just leave it as a default. And just so you know, by default, we're not doing this. We're just fetching getting the factory from the runtime. So we're getting the same data buffers that the runtime underneath is using to write and read from, and to requests and responses. So we're plugging into the same mechanism. So once we have that factory, we can allocate a buffer, and once we have that buffer, we can write like exchange. And we need to get the bytes with a standard car set, and let's go UTF. So yeah, you probably won't do that very often. And once you've written that, you've got the data buffer ready, and then you can write it. Obviously, you can write more things, etc. No, sorry, there'll be a mono of just buffer. So here, and we are returning this. So in detail, so we're getting the response. We could get the request as well from the exchange. We are setting the status headers, and then we're allocating memory, and we're writing that to the response. And as you can see, that method is not doing anything. It's just preparing the pipeline. We're really writing things when the response is ready to be read by the client. So if we get back to Exchange, we'll have that. So not something you use every day, but that's how it works under the hood for allocation, etc. The next thing we could do is one interesting thing as well is is how you can see, in the first part with Sébastien, we've seen that we're somehow controlling time with the publishers. We know when things are published or completed. We can wait a long time or not. And we can have things like this. For example, we could have a mono of string, and we could return a mono dot never, just to troll our users. Why is it complaining? Mono string, yeah, no, you can just return mono then. No? Ah, yeah. Stupid me. Yeah. So if we do that, then we can see that we're just waiting, and it's not happening. Nothing is happening actually. So it's not something you want to do, obviously, but it's a way to show you that with the publisher, you're controlling the way the data is written. You're controlling the connection, the state of the connection, and it's more to just the value we're publishing. It's a lot more.
Yeah, in fact, we translate the reactive API semantics to something that matters for that case HTTP. After we will see servers and events and other example, and that allow to basically control the data send, the flushing. You have talked about the nested publisher, where the complete signal of the nested publisher is used to know when you flush the data. So we try to reuse the semantics from reactive streams and apply that to the web.
So we can as well, when something bad happens in our code, we could have an error flowing through the pipeline, and when that does happen, we have. Let me show you. We have this. So directly, the framework is fetching that error if we don't have exception handling mechanisms set up. We're just getting that error down the line and translating that into a server error. So those are the basic things you can somehow expect when dealing with a controller. And but now we'll switch to the real part of the application. So the next part we can do is I guess we'll go with the first view. So what I've got right now is in my application, I've used FreeMarker as a templating engine, but we'll talk a bit more about those later because you can use many others. So you can use a templating engine, and the difference here between this and Spring MVC or other frameworks, it's everything happen. All the processing happens asynchronously. So you have to resolve the view asynchronously. You have to provide all those things. So what we can do, we can set up the whole thing. We can have a web configuration class. We can say that it's a configuration class. We've got a new web reactive configurer, which is an interface. And in there, we can create a FreeMarker configurer, which is something that you need to resolve views, etc. So there you go. So we're resolving views from the class path from the templates directory, and then the important part is to have a view resolver to install that view resolver. So we're activating the FreeMarker view resolver. Once we're done with that, we can we can go to the dashboard controller. So we've got a different controller. That's the controller of our application. And here we just want to have a view. So because it's totally synchronous and we're not doing anything, we can have the home view set up like this. We just say that we have home mapped to /. So nothing really fancy here. But just so you know, we're resolving the view like this and asynchronously resolving it on the class path or whatever, and rendering it as part of our pipeline. So still the expected behavior, but this is how things can be done. So right now we've got the first part of our application.
Yeah, that also means that in the future, if you have some, I don't know, a microservice application that exports the template, the view resolving side and the template side in an external microservices, since everything is asynchronous and reactive, that's doable here, where with regular Spring MVC application, that won't scale.
Yeah, totally. Next thing, we can use an actual repository to deal with the database. So that's what we'll do. So that application right now is using a few specific things, including snapshots again, of Spring Data MongoDB, and a specific Reactive Streams driver for MongoDB. So just so you know, right now in the Spring portfolio, we're working hard on adding a lot of support for everything reactive related in all the portfolio. But on the Spring Data side, right now it's Mongo and Redis and Cassandra, Couchbase maybe.
Couchbase may come later, yeah.
And Kafka, but not maybe in Spring Data. Not sure. Anyway, especially NoSQL data stores, they have those reactive drivers. And on top of those drivers, we can have that. If you don't have that kind of drivers, it's really hard to, or you have to fall back to what Sébastien showed with going to the blocking world. So once we have that, we can we have an existing repository. So it's a reactive CRUD repository of a Reactor person. Reactor person is ID and name here. It's just that, and that CRUD repository is having the real signature types that we saw earlier in Sébastien's hands-on. So we have the save methods, find one, etc., with mono and fluxes. So this is the kind of repository you could expect in the reactive world. And right now we can, for a start, we could create our application. At the start of our application, we could create some data. Let's do that. So in our application, right now Spring Boot supports a command line runner, which is if you create a bean that implements that, that bean is being run when your application starts. And this is something that is blocking for now because that's the semantics attached to it. But so that's a good example for us to do things. So we'll create a bean like this. We want a command line runner to init our database and to create a few things. So we'll fetch so that command line runner is taking the arguments that are given to your application when you start your boot application, the arguments, the command line arguments, but we won't really use them right now. And we'll use a flux of reactive people right now, like this. So we have a reactor people created with a flux just, so a flux of people working on Spring and Reactor, RxJava, etc. So those people, we'd like to first delete the database and then insert those into the database. But the whole thing is blocking. So it's not really important because it's done at the beginning, at the start of our application, not as part of handling a request. So we can safely do that. So I'd like to get a hold of the Reactor person repository. And since it's injected, I want to delete everything from that database. And then I'd like to insert that flux. So there are a few things we could do. If we do then, it's waiting for mono, because right now we're we have a mono. We're building on top of a mono for that pipeline. So we could use either a mono, or we can have a then many if you have a publisher. So here we want to delete, and then we want to insert everybody into that database. So we'll save our people in that database. So now we have got the pipeline ready, but we need to be blocking, because if I just do that, nothing will happen. Nothing will subscribe to that pipeline. So the application will start, but nothing will be in the database. So if I want to do that, I want to block for the last emitted element. So when I do that, when the application starts, the data is being written to the database and deleted, then we insert everything into the database. So that's one way to deal with things. And we can actually check that it's working properly by setting up things. So we've got already our repository. So we could have a get mapping with a reactor, people like this. And we're expecting a flux of a reactor person, which is public. And then it's like final, and we should return repository.final, which is a flux of reactor person. So doing so, it will return those objects, and those objects will be emitted one by one. Those users will be emitted one by one. So right now, I don't think that we're supporting live queries, MongoDB live queries, but you could imagine plugging that into MongoDB live queries and have things as they arrive into your database. So there are many use cases here that we could many things that we could do.
Yeah, for Redis push feature, for example.
For PubSub, yeah, since it's a stream, it's not just an asynchronous list. Somehow, it's you can really control the time of when things are emitted or not. So doing so, we'll get a flux of those objects, and those objects will be serialized one by one and emitted and written to the response as they come. So it's really, we're not buffering everything in memory, all those users in memory. We're just writing those as we can.
Yeah. Here in theory, that would be nice to be able to use a full reactive serializing library. Sadly, Jackson does not support that currently. That may come in the future, but currently that's not the case. So what we are doing is calling the existing Jackson serializing method for each element. That means that you could theoretically deal with an infinite stream, an infinite flux of elements, and we are calling the Jackson method on each element that allow you to deal with very huge collection in stream way. If you are dealing with huge elements, very complex to serialize, you will begin to have some issues. So that's the current status, because we don't have a good reactive JSON serializing library. But everything is ready. As soon as there is a reactive version of Jackson or any other serializing library, we are ready to integrate that in Spring Web Reactive and do a fully asynchronous and non-blocking processing. So that's an intermediate state, because, like usual, the ecosystem has to evolve, and currently not everything is ready, so we do our best to integrate what we can.
Yeah, exactly. So it's so we do have that response right now being written to the HTTP response, and we could add another mapping, this time for a given person. So doing something like this. We always have, we're expecting the response body here, and we're expecting just one person, and this time we're returning a mono. And we are here, we're having a part variable, which is the string ID. And we can then return our repository find1 ID. That should work. So if I do this, I'm getting a single response turned to the database. So, okay, but if I do something like this, I'm getting an empty mono, which is totally empty, but it's not an error. So I'm getting an empty response with a 200 status. And we may not want this. So in those cases, we could build some kind of operators on top of it to do things. So it may not be the way to do things really in application. It's just to demonstrate how you can use those operators we saw earlier, how you can use those in an application. So, for example, I like to do something when it's empty. So I could provide a default reactor person and make a new reactor person here, and that'll be provided if I'm not finding anyone. Or I could do otherwise if empty and maybe look for that person in a different repository, or even in that case, throwing an error. So I do have a
Reactor not.
Is it a reactor?
Reactor not.
Person not found. Yeah, great name. With the ID. So if I do that, this time there'll be an exception flowing, and the exception flowing will not being handled will result in a 500, like expected. So we could do something like exception handling. So we're handling here the reactor person not found exception, and we can return a response entity of a string or whatever, or just a response entity actually, and handle not found exceptions. And we could return a response entity with not found build. Yep. So this time we'll do get the 404, the expected 404. So here we could have also other signatures, a response entity of a mono or a flux of something. We could have a mono of a response entity or a mono of something else. So we still have those flexible signatures. It's just that right now, on top of all that, at any time you can build on top of your pipeline with operators, and you can do more things. So we can imagine other ways to obviously deal with the fact that we don't have one person, not necessarily use exceptions, but that's one way of dealing with things. The next step is, what is it again?
Call remotes.
Oh yeah. So in our application, we've got the issues tab. So we'd like to use the GitHub API, fetch the current issues for the Reactor project, get those and serialize those as part of our HTML view. So that's a remote call and a bit of buffering for things, and you'll see how it goes. So for all that, first I'd like to go to use the dashboard controller. So in our controller this time, I'll just map to issues and just return the name of the view. So once we click on that, nope, 500, what happened? What's happening? I think I'm probably missing. Yeah, the template can be rendered right now because I'm missing things. It's just expected. So the next step is to use the dashboard service, because I'd like to actually fill in the model here. I'd like to get the model, which is the way to add things to the view while it's being rendered. And I like to do model and add an attribute, add something called issues with the list of issues. To do that, I need to go in my dashboard service, which implements a few methods. So the first one we'd like to implement is the find reactor issues. Here. So we've got our default implementation for the dashboard service, and right now it's just returning flux of empty, so no issues at all. Yeah. So for this, to fetch the issues, we need to use the GitHub client, and that GitHub client right now is doing nothing. So to do that, we need some kind of REST client. Technically, we could use REST template, but we chose to implement a totally new client in Reactive Web because it's very useful, and going from blocking to non-blocking all the time is just really, really hard. So we created a web client. That web client, we'll create that web client right now. So to create a web client, we need to create it and provide a connector. So right now we have a connector, which means the underlying implementation with the real HTTP client under it. We're using the Reactor Netty client. So an adapter and more Reactor on top of the Netty client, HTTP client. So we're creating that, and now it's ready. But we could do a few more things because when you're using GitHub, you need somehow. I mean, either you're sending those requests and you'll have the default rate limiting API, which can really go really quickly. It's only 60 calls per hour, something like this. So in our case, we'd like to add some headers to our request, some basic authentication to our request. So what I did before that, in our application.properties, I added some properties that are dashboard. No, was it GitHub? No. Anyway, I've got those properties handy, and it's dashboard properties. So it's a class where we're storing the GitHub, the GitHub and Gitter tokens, authentication tokens. So it's being read from the Spring Boot properties. I won't show you my private key, obviously. Let's go back to the GitHub client. So we'll inject those as part of our client here, and we'll use that to add something. No. Was it create or is it something? No, it's builder.
Builder, yeah.
Because I want to add more. On top of that, I can use some strategies. So those strategies are about serialization, deserialization. But here I want to add a filter. And as you can see, that client has some kind of a functional style and builder pattern, immutable taste to it, and it's done on purpose. So we can. We provide some already defined filter functions, and one is the basic authentication. So we can do properties, GitHub username, and properties GitHub token. So this is one filter to add to every request going out. We'll add the basic authentication header, and then we can build. One more thing, if you're trying to make remote REST calls to the GitHub API, if you don't have a user agent provided in your request headers, the GitHub API will complain. So we can actually build another filter of our own. We'll build it right here. So it'll be an exchange filter function. and we'll call it a user agent. And so we'll implement that, and that exchange function can do something to the request and provide the request to the next function in line to execute the request in that pipeline. But because requests are immutable in our world, if you want to create a new request, you need to create it out of the out of the previous one, and we can add some headers. In our case, we want to add a header called a user agent, and we can call us Spring. Doing it build. Good. And then when we're done building that request, we can pass it to the exchange function and exchange the new requests here. And as you can see, the return type of this is the mono of a client response. So we're expecting one client response as part of a pipeline. So this is our client that we will use. And now we need to find the open issues and call the GitHub API. So to do that, I'll use my web client, and I can web client exchange? No, yeah, that'll be it. So I can create a request first, and that request will be a client request dot get, and we'll have a GitHub. We're using the GitHub issues URL, and we're providing the owner, which will be the Reactor repository and the repository itself. And build. So we've got a request, and now we could use exchange, and we could provide that request, and that returns a client response. So from that client response, we get the full response. We could extract what we need from it, but a better way to deal with this is to retrieve a flux, and we're directly getting the body. So we want a flux of GitHub issues, and there we go.
Yeah, you need to add an accept with the right content type. I think.
Right. So yeah, thanks. So that'll be the
BND GitHub bit free.
Yeah. So we can provide an accept header to that one, and that'll be here headers. And no, it's just header.
Dot accept directly.
Oh, yeah. Accept, and we can call it BND like this. Okay. So when we do that, we're creating a request, sending it with the client, and we're getting a flux of GitHub issues in response. So under the hood, we're sending the request, getting the body, and because we have a Jackson under the hood, we're deserializing every GitHub issue JSON in JSON format, deserializing it, and feeding that to the outgoing flux. So we do have one flux going out, and we can consume that right now. So if we go back to the controller, I guess, dashboard controller, we can use that. And we can use the service and to find Reactor issues, and we have this. But we somehow need to get all those issues into our view. And the problem is it's a flux. So right now in Spring, in Web Reactive, we're supporting FreeMarker, which is a regular templating engine. And if we were to give a publisher of some sort to FreeMarker, it wouldn't like it because it doesn't know how to deal with it. But just so you know, there are other templating engines, including Timeleaf, that are working on supporting natively those publishers. So you could provide publishers to your templating engine, and the templating engine would consume those while rendering the actual template. So that would be way easier. But because we don't have that right now, at least in that demo, we need somehow to figure out a way to get the list of everything, but we don't want to be blocking anyway. So what we could do is know that because we're doing something asynchronous, we don't want to have return just string. That would be just very bad because we're actually calling a REST API behind the scenes. So we don't want to do that. But we want to provide that list. So what we could do, we could collect this as a list. So we get as you can see, we're getting a mono of a list of reactor issues. So we're buffering all the reactor issues and emitting a single element, which will be a list. So we're collecting everything. And here we'll need to provide the name of the view as a return when we're returning things, but we still need to add things to the model. So to do that, what I'm doing this. I'm
.zen after the collect lists.
Yeah.
And
so
after returning a mono.
Yeah. So I've got the mono of everything with the list inside, and I've got to concatenate this. So when I'm doing then, I've got the list here, so I've got the issues, and I can do something with them. So what I could do is add them to the model. So I can add that attribute. I can add those issues to the model, and then I can return the name of the view, which is issues. Right? So in two parts, we're fetching the data and we're collecting it into a list and putting that into the model as we do, as we're executing things, and we're returning the view. So just keep in mind, if we had a rendering templating engine that supports publishers, we could just put the publisher inside the model and return issues, return string synchronously, and the rendering phase would subscribe and would do the whole thing safely. But because we don't have that, we have to.
Yeah, and that will achieve live rendering of the template.
Yeah, exactly. So there are use cases where you could imagine huge templates, and that could be very handy if you have like very, very long templates and big pages. So rendering things asynchronously instead of gathering all the data in memory and waiting for everything to be ready to start writing your template, you could just start writing the template as things are made available. So, for example, writing a huge list, that could be really useful.
But you are going to see a fully reactive push example just after with the Sébastien event example.
Yeah. So here, I'm just using Lambda better. So we've got our issues? No? Yeah? I did something wrong probably. You know what? Let me cheat. Because probably a typo somewhere. That'll be in version control logs. And check out revision. Force. Here. Okay. So here's the full thing with all the issues. And one thing that I'll show right now is something that I didn't write while doing that. It's the controller. Okay, I've got the issues right now. Okay, and what we need to show is that in the default dashboard service, I did something more. I'll show you. So I am using in the dashboard service, I am calling the find open issues using the client to return the issues. That's the part that I totally didn't implement previously. So I need to get the issues, and I could just return those and map those as Reactor issues. But what I'm doing here, and that's what we could actually do to really show you how it goes. So I could use the GitHub client, find open issues on the Reactor org and Reactor Core, this, and map those to the actual type I need. So for one issue, I need to translate it to a new Reactor issue type, because this one is a GitHub issue. So this one is taking two things: one GitHub issue and an online status. So that online status is saying whether that person, the person that created the issue, is right now on Gitter, on the Gitter channel for Reactor or not. So by default, let's say we say false because we don't support this. So if we do that, by default, we'll see that all the icons are people not being there, not being online. So if we want to do several things at the same time and concatenate several calls, that's what we're doing here. So first, we'll get the issues. And then, because for every user, for every issue, we want to get the username of the person that created the issue, and we want to get the list of all the persons connected to the Gitter channel, which is right here, right now. So we want to get the names of all the people connected to that Gitter channel right now using the Gitter API. And we want to know if they're online or not. So to do that, we'll use another client that we created. So this is the Gitter client. So this is basically the same as the GitHub one. We're using the web client to make remote calls and deserializing things as they come. So in that default service, we'll get those issues, but because because we want to know that status for every issue, for every person, we want to make sure that to have the whole list. So here we'll get the users in the room, in the Reactor room, with a maximum of 300 persons, for example, and we're collecting everything into a list of Mono. And here, so I'm a bit cheating, but explaining things. So here, because I can't really zip things, if I wanted to use the zip operator, I would have one GitHub issue and then one Gitter person connected at a time, and that's not what I want. I want for every issue, I want the whole list. So that's why I'm using the users. I want the whole users, and then I want to flat map everything. So I do have the list here, and with that list, I'm using flat map because for every user list, I'm getting just one. For every user list, I want to create a flux of issues. So flat mapping will just, as we've seen in the first part, we'll just flatten the publishers into a single one. So once we have that, we want to map all our issues. So that was the issues we had. So for every issue, we want to know who created the issue and if that person is currently online. So we've got the user login from the issue, get user, get login, and we'd like to know if that person is online. So to know that, we have the list. We can stream it and filter it to know if the user, if the user equals the GitHub user, the name we're having. So we're getting the user, his username or her username, and we're seeing if it equals the user login we had previously. So this, and then we'll get just the first. So here we're trying to find if someone is connected with the same name. And so here we will get an optional of getter user, like so. So we have the optional of getter user, so we can, as previously, we can map it to a real a reactor issue with the issue we're having, plus before we were just doing false for everybody, and now we do have the we do want to know, we know if the user is there or not with the optional.
Sorry.
Yeah.
How many concurrent threads are actually handling that one request?
There are, the question is how many concurrent threads are we dealing with when we're sending those requests? We're dealing with one, actually. So under the hood, Reactor is using the LMAX disruptor, and a variant actually right now of LMAX disruptor. And so you have one thread, and you don't have one thread per request or per. So you're using a Reactor, the Reactor pattern. You're using an event loop under the hood. So you have one thread and dealing with events and with selectors or things like this. You're aware of things being available to you with events. So it means that you can send a lot of requests, and it will be you're not relying on the thread pool. That's it, basically. You're just relying on all of this. As long as you're using that client and doing things on top of the that reactive APIs, you're not relying on a thread pool, and you don't have those issues anymore. So the REST call can take a lot of time. You won't be bothered. It won't really matter for your infrastructure.
I think by default that's one thread by core, basically, that is configured.
Yeah, to be more efficient, right? So if I do that, back to this, we do have the status of everybody involved. We do have the both the issue here and as well the online status of the person.
Stefan is always online.
Right. So we're done with that part, with the issues part, and now we'd like to do something more. We'd like to show the chat, what's going on in the Gitter chat of Reactor. So right now people are talking, I guess. Stefan is talking. What we can do is still use the Gitter API, but here it's a bit of a different use case. So the Gitter client is already implemented, like I showed you. So we've got get users in room. So that's what we're using to see if someone is connected or not. We've got a find user in room, and we've got two other methods. One, that's the first one we'll use, is get the latest chat messages. So with that, given a room ID and a number of messages, we can ask for the X latest messages in that room. So we'll use that in our dashboard controller to create a new mapping. So first we can map like chat. That'll be the view. Right. Then we want to add another endpoint, which will be chat. What is it again? Chat messages.
Chat messages, yeah.
Yeah. So public. We're returning a flux of Gitter messages, and we can safely return this getter client. No dashboard service. Sorry, and we want the latest messages. So here we could say, for example, let's have a request param that is not. Yeah, okay. That is not required, and the default value could be something like 10, and it's called limit. That's the string. And so we could have like integer parse, something like this, the limit. Okay, so if we do that, we do have a new REST endpoint, which would be a response body. So if we do chat, we have the view, which is empty right now. And if we do chat messages, it's empty now. Is it? Is there something wrong? I forgot to implement. Yeah, again. So here, this getter client, and get the latest messages. And so this is probably in our properties, getter. We want that'll be the room ID. So we want the room ID, and then we want the limit, which is provided. So we want the latest messages for the reactor room with a limit. So this time we should have like the latest messages, right? So those are the messages and the user information we're getting from Getter right now from the API streaming. But the thing we'd like to have is something more useful. We'd like it to have here. So to have that here, we could use our view. So this is our view. We've got we've got some HTML, and we'd like to do that with an AJAX request. So I prepared it with a random jQuery code, but you can use anything you liked. So we're fetching the latest messages, and we are adding those to the DOM once they're ready. No? Typo? App and chat messages not because I put it in the right. Thank you. Come on, right. So we've got the latest messages, but so this is the part where we're using a Flux as an asynchronous list of some kind. So we're getting the messages and we're adding those because we're getting those from the AJAX requests. But like we said, Flux can also have another meaning. It can mean a stream, like a stream of messages. So if we go back to the dashboard controller, here we're producing. Here we're producing JSON, right? But we could stream the latest messages. So we could have the get mapping for this time chat stream. Same thing, a flux of getter messages. And this time we can return this dashboard service, stream chat messages. So this is still a Flux. And if we go to our default dashboard service, we can still use the getter client, and same thing. We can ask it to fetch the stream, and with the reactor room ID. And if we look into that client, we'll see that we're not using API.getter, etc. We're using stream.getter. So it's stream-oriented API. So the response is kept open by Gitter, and they're streaming messages as they come. And we're plugging that directly as a Flux into our client, and we're returning that with our controller. But since we definitely want to have the stream meaning here, we'd like to here produce media type, which is different, because it will be a text event stream. So we're doing SSE here, server sent event. So once we do that, we still have the same thing, right? Here in the network, we still have the same thing, and we have the live reload enabled, but we're fetching the chat messages, but not the chat stream yet. To enable that, we definitely want to go to there, and we like to, was it SSE? Yeah. So we're using the plain server send event JavaScript API, creating an event source to the chat stream endpoint, and we're appending messages to our view as they come. So same thing. If we reload, this time same thing, but we do have the chat stream here, which is pending. So the request is being kept open. And if I, yeah,
just send a message.
Right. So this is being sent from the Gitter API and fed through the Flux and as a server send event to our SSE connection. So it really shows how you can have, like, Flux can mean an asynchronous list of some type, but it can mean many more things.
Yeah, and the web client that you have built can be used to request regular REST endpoint, but can also be used to request some streaming-oriented API, where the JSON objects are just serialized as they come, and the input decoder will automatically identify each JSON object and will pass them through this kind of Flux-based API, and that goes through the server-sent event endpoint that we have seen.
Yeah. So we're done with the live coding, and we've got a few things to share with you with our experience with React 3. So the first thing we went through is that we needed to change our mindset, and it takes a long time. You have to really enforce the fact that you should do non-blocking everywhere, and especially when thread boundaries or I/O boundaries are involved, so latency, etc. So for us, it meant using servlet async I/O. It meant using Java and I/O channels and not using blocking APIs inside the framework. It also means that we needed to revisit and reconsider some concepts. For example, if you try to think about thread local, transaction, or any global state in a thread, it doesn't really apply anymore, because at any given time, your processing can be transported to a different thread, because we've got like four threads, or if you've got a 4-core CPU, so the execution can happen on any thread at any time. So you can't really rely on those things anymore. We also had to really agree within the team with some terms like async, non-blocking, etc. It doesn't matter if the whole world doesn't agree on those. You really should agree within your team with those terms. What do they mean? When those happen, etc. Because otherwise, it's really hard to work on those things. To reiterate from what Sébastien said earlier, you shouldn't ever re-implement yourself the React Streams interfaces.
Yeah, at least publisher.
Yeah. Subscriber you can somehow. But if you look at the Reactive Streams Commons project, you look at the code, it's really involved. So it's definitely not easy to pass the TCK. So you definitely need to pick a reactive library and use it within your application. And also Reactive Streams by itself, it's for interop. It's not enough. As you've seen, with a really simple application, we needed operators to do things, transform, timeouts, etc. So you definitely need an API. And also, like we've said, when you're setting up the pipeline within your, for example, controller methods, as long as nothing subscribes to it, nothing happens. So within the web framework, we're doing this for you through the web layer, but if you're testing things, if you're not using a step verifier, if you're trying things manually, you should subscribe, otherwise nothing will happen. Nothing will happen. Concurrency, we had a few of those. When they do happen in your code, it's really, really hard. So you have to deal with it and really fix those. And for that, it's usually easier to deal with those issues if you have good libraries. So a good reactive library. If you have, if you're also using selecting good libraries and drivers and APIs that are reactive streams friendly. Otherwise, it's way harder to deal with things. You should really have good tooling, and I don't know if I showed that, but with Reactor, by default in dev mode, right now in Spring Boot in dev mode, we're activating something that is costly, but so you shouldn't activate that in production. But that thing is collecting the stack traces when an error happens. And when something bad happens, you definitely have the right line and the right class where the error happened. Otherwise, if you don't have that activated, you're just getting a stack trace with many operators and callbacks, etc., and you don't even know where the actual error happened. So if you have good tooling, you can have those kind of things that are really helpful when you're developing an application.
Yeah, in Reactor we call that stack trace mode.
Yeah, stack trace mode. So it has a performance penalty, but in dev mode it's a must-have really.
Maybe just something about the ecosystem. As I said, the ecosystem is currently evolving. So not every database, for example, has a reactive driver. Some of them have Eric Java 1 based driver, and the ecosystem is slowly evolving toward moving to a reactive streams based reactive API. And that will take a little bit of time, but currently we try to adapt from Eric Java 1 to reactive streams, that's possible. And slowly, I think various database or HTTP client or thing like that will provide some kind of reactive streams based API that will fit perfectly in that.
It will take some time for the whole portfolio to catch up.
Yeah.
So don't create issues all over the place saying it doesn't work. It's just because it's not done yet.
Yeah, at least the foundation are really designed to be compatible with such reactive template resolution, reactive serialization, for example, and when the ecosystem will be ready, that will be integrated directly.
But collectively, we definitely need to push the whole community to adopt this and at least adapt to it to provide some kind of tooling or drivers for all the databases and whatnot. So here are the links of everything. So the Project Reactor, if you want to know more about this, it's at Project Reactor on Twitter and projectreactor.io. The two repositories we used for this, so the hands-on, the first part is located within the Reactor organization. You can redo it and use that as a regular hands-on to really get a feel of the Reactor API. Yeah,
you have two branches. You have the master branch that I use at the beginning, and you have the complete branch with all the answers.
Yeah. The second part is in the the third link here. So it will probably evolve because we're still working heavily on both Spring Boot and Spring Framework on this. So it will get better. And there's an interesting blog that you wrote, I think, about the reactive types. So it's a longer version of everything you said about the JDK8, RxJava types, etc. If you want to know more about this, it's really useful. We're almost at the end. If you want to know more about reactive web in Spring, you can check out that session on Friday, given by our colleague Rossen. Friday morning. And if you want to know more about Spring, everything related to Spring, there's a BOF Wednesday evening at 7 p.m. I think we're done. If you have questions, go ahead. Don't hesitate. Otherwise, you can come later and ask. Yeah. Yell, and I'll repeat. Can you talk louder? I'm not getting the last part of the question.
To the question after.
Or you can ask that later. Was it about the templating? You're wondering if it's really useful to do server-side rendering with a reactive application? So with, I'd say with TimeLeaf, it really shines because the TimeLeaf team has worked on this, supporting publisher and having some nifty use cases where it's really interesting to use this. So it's not only rendering big pages, it's also trying to do a clever thing with performance. So dealing as well with buffers, reusing buffers when they can, etc. So it, like you said, it really shines when you're having a REST API or a service-end events or something like this. But for server-side rendering, you still need it, and it can have some upsides. But you're right, it's not changing the world for that part.
Yeah. If you have any other question, come to talk with us. And thanks, and have a good lunch.
Yeah, thanks.